Let's take a look at some typical collisions that we might see in a physics classroom using our common equipment that is found that involves some carts that are sliding along a track. So this video is just a collection of some different carts. You should notice that sometimes the carts are empty, so they have the same mass. Sometimes they have an extra mass on them. You'll see that in a second. Sometimes they bounce apart. Sometimes they stick together. Sometimes they start from rest and sort of explode apart. Okay, so there's lots of different situations being represented here. What we're going to be focusing on is how can we analyze these sorts of situations? How can we predict what is going to happen? Now, you might be thinking, oh, well, how about energy? We just talked about energy being conserved within a particular system. The problem here is that when you have collisions, there's often going to be some sort of deformation of the objects. Think about a car crash and how the bumper sort of scrunches together. That's sort of like an elastic potential energy, but it's energy you can't really get back. Or a typical collision, you're going to hear things crash into each other. Sound is actually a form of kinetic energy, but it's the motion of air. And again, you can't really track that. And then lastly, all sorts of interactions have some sort of thermal energy that's involved. Kinetic energy of particles and molecules as they get heated up because of the interaction themselves. So basically, energy is not going to be the best method for us to be looking at here. We are going to use something called momentum, which is a more trackable quantity, and we're going to see that it really will work for what we're trying to do. So Newton had a way of describing momentum as being a quantity of motion. But to really put that into words, recognize that momentum involves an object's velocity and its mass. Now, of course, we had kinetic energy that also involved those two things, but energy did not incorporate what direction something was moving, and momentum does. And that's really the benefit here. It's going to allow us to analyze situations that we wouldn't be able to analyze with energy. This is the formula for momentum. The P stands for momentum. I know that's kind of strange, but we can't use M. M is already mass. Okay, so P is what's been chosen. The units are just found by doing the same thing to the units that you do to the numbers. So we'll be multiplying mass times velocity, and mass would be in kilograms, velocity would be in meters per second. So our units are just kilogram meters per second. Notice there's also some arrows included in this formula. Remember that indicates that the direction of these quantities makes a difference, that you should pay attention to them. They are vector quantities. Very important part of what we're talking about. It turns out that in all the different types of collisions I just showed you, momentum was conserved. It is a quantity that no matter what is happening, and this is kind of amazing, no matter what is happening, any sort of interaction, the momentum of the system stays the same. If we can find the total momentum before, it will always equal the total momentum after the collision or the separation or the explosion, no matter if we lose energy to something, some sort of form that we can't easily get back. So I want to prove this to you and show you where it comes from, but I do need to remind you of something that hopefully you've heard of before, but we haven't spent a lot of time on in this class, and that is Newton's third law of motion. Quick recap of the laws of motion we have talked about. The first law, also called the law of inertia, deals with equilibrium. This is when forces are balanced on an object and there's no change to the object's motion. We learned about that in the first semester as well as the second law. And the second law said, well, if you have unbalanced forces, then something's going to change. There's going to be acceleration. So we had this formula, sigma F equals ma. The third law is all about interactions. So it's not just focusing on one object. It tells us that all forces come in pairs, that they're always one part of an interaction. That if object A exerts a force on object B exerts that exact same amount of force, same newtons, back on A, but it does it in the opposite direction. You may have heard this as for every action there's an equal and opposite reaction. That's kind of an everyday way of saying the same sort of thing. But the key thing is to focus on the amount of force and how there are always two forces involved. One on, acting on two different objects, and that the forces are the same amount or magnitude, but opposite in direction. Here's a number of different interactions where we could sort of see this in effect, where we have one object that it seems like they're exerting a force on something else, kind of representing this green arrow. But in reality, you can't have this force without having the opposing force. The forces always come in pairs. That's what an interaction refers to, that there's this combination. But notice how the arrows are always pointing in opposite directions. They're always the same length, representing the same size or magnitude of force. That's what we're going to use as we move into or return back to collisions and see if we can apply this to the collisions of two carts and see how this affects the motion or allows us to predict the motion. So why this matters in a collision is that regardless of how big the truck is or how small the car is, what speeds they were going at, they will each experience the same value of force. It'll just be in opposite directions. The truck will be pushed to the right and the car will be pushed to the left. The other thing that's going to be important is the impact time. They will feel the same force for the same amount of time. There's this interval when they're connected, when they're exerting these forces, and it must by definition be the same amount of time. Now you might be saying, now wait a second. I've seen crashes before, and this little car is going to get smushed and the big truck is going to seem like nothing happened. How can we say that the same forces have been acting? Well, we're not saying that the effect of the forces is the same. Because F equals ma, the acceleration is going to be the force divided by the mass. And so this big truck with a bigger mass is going to have a smaller acceleration, a smaller change to its motion. And the smaller car with a smaller mass, F divided by a smaller number, is going to give a bigger value of acceleration. They're inversely proportional. So we're not saying that the effect is the same. We're saying that the forces on the objects are the same. Let's dig a little bit deeper here. Again, Newton's second law was F equals ma. We're just looking at the interaction forces. We're not worrying about all of the forces for this situation, so I've dropped the sigma from there. Recall also from first semester that the acceleration can be found by looking at the change in something's velocity and then dividing by the time. Now I've included the arrows in these formulas to be a little bit more formal because, again, direction is going to be so important with what we are talking about in this section. Let's do a little algebra. We'll plug in the A formula into the F equals ma formula. And then I'm going to multiply both sides by t, kind of rearrange things a little bit, and I get this idea. Now, this helps us define what's going on in terms of momentum. So the right-hand side of the equation is really just the change in something's momentum. M times v, but the m won't be changing. It's just a single object that we're looking at with this formula. So it's the velocity of the object would be changing. But over on the left, we have this new quantity, force times time, which you might remember. I just said how in a collision, each object feels the same force for the same interval of time. This is called the impulse. The impulse is related to the amount of force acting on an object, but it says a little bit more. It includes how much time that force is being applied. And what that impulse does is it causes a change in momentum. So in the same way that forces caused change in just motion, caused accelerations, we can instead kind of flip it a little bit and say that this impulse, Ft, causes a change in momentum, m delta v. Let's see how this works out with a few sample numbers. So if you have a force of 20 newtons acting on an object for 5 seconds, we could calculate the impulse as 100 newton seconds. Again, with this formula, because we are multiplying the numbers, to get the unit, we also multiply the units. So that's where the newton seconds comes from. By the way, the symbol for impulse is a capital J. It's kind of an unusual letter to use because we've just gotten through the fact that like the unit J is joules, and so that can get a little confusing. We don't actually use it all that often, so if you want to just write the word impulse, that's okay too. Let's see how this impulse affects two different objects and helps us predict their motion. It depends on what the initial state of the object is. So we're going to look at two objects that actually start with the same amount of momentum. First, we'll look at a 40 kilogram object moving at 2 meters per second to the right. And remembering that momentum is m times v, we'll just multiply these numbers together and let's call to the right our positive direction the way we often would do. So this would be a positive 80, and then again the units for momentum, you just multiply the units that you were using, so kilogram meters per second. And then this impulse happens. Okay, so this impulse is applied, a force during a certain interval of time, 100 newton seconds. And that's going to give us a new amount of momentum. We're going to add together that 100 to the 80 to get 180 kilogram meters per second. So now this 40 kilogram object has that amount of momentum. If we divide by 40, we can see that the object would be moving at 4.5 meters per second. All right, before we look at a second object and sort of see how it affects that, maybe you're asking, wait a second, how can you take kilogram meters per second and add newton seconds and then go back to kilogram meters per second? Let's take a quick look at the units. So remember that a newton is a mass unit times an acceleration unit. So kilograms times meters per second squared. So if we are working with newton seconds, we would want to take kilogram meters per second squared and then multiply by seconds. So one of the seconds will cancel out, and look at that. We are back at kilogram meters per second. So a newton second and a kilogram meters per second are really just two ways of describing the same thing, the same unit. Just for impulse, we tend to use newton seconds, and momentum, we tend to use kilogram meters per second. Either one is correct. All right, back to our discussion here. So let's now take a look at a different object, but an object that actually has the same amount of initial momentum as the yellow one up above. So this one has a mass of 20, but its speed is higher, 4 meters per second. So they have the same amount of momentum, 20 times 4. And so if we apply that impulse of 100, we're still going to end up with 180 units of momentum, 180 kilogram meters per second. But now it's a 20 kilogram object that has that momentum. So if I wanted to figure out how fast it was going, I would take 180 divided by 20 and see that it's going at 9 meters per second. So impulse determines the change in the momentum, but there's still more to the story in terms of how big the object is, what its mass is, and how fast it's going. Let's apply the same idea to a collision. Okay, so we've got a truck and we've got a car ramming into each other. We'll use some typical values as we go. We'll assume the car has a mass of 500 kilograms. The truck is much bigger at 2,000 kilograms. Okay, so we'll see that these numbers in a little bit here. But let's say that the impulse is 8,000 newton seconds. Okay, so the combination of force times time during the collision is 8,000 Newton seconds positive. So if I looked at the car first, okay, so the car, again, we're going to say it has a mass of 500 kilograms, pretty typical for a car, and let's say it's moving at 10 meters per second. Now notice that based on the direction the car is facing, it would have been moving to the left. And so when I take mass times velocity, I'm going to assign that a negative value. Okay, my momentum needs to have a direction to it as you're working through these situations. And then this car feels this impulse of 8,000 Newton seconds. So its momentum is now positive 3,000. Wow, so this collision is actually changing the momentum from being a negative value to a positive value. But that should make sense. If you've ever seen a collision between something big and something small, a lot of times you see the small thing get, pushed backwards. And so taking 3,000 divided by 500, we would see a positive number for the new velocity of the car. All right, let's turn our attention to the truck. The truck is bigger. It has a mass of 2,000 kilograms, but we'll have it going a little bit more slowly, lumbering along the street. So it's going at 5 meters per second, but again, the way it's facing, it's moving to the right. They're heading towards each other. Its initial momentum would again be found by taking mass times velocity. 2,000 times 5 is 10,000 kilogram meters per second. Now, it's going to feel the exact same amount of impulse, 8,000 Newton seconds. However, the truck pushes to the right on the car. That's why this was positive. But the car pushes to the left on the truck. So again, Newton's third law, equal and opposite ideas. It's still 8,000 Newton seconds, but we would assign it a negative value because it points in the opposite direction. To find my new momentum, I would combine 10,000 initially with this negative 8,000 impulse, and I would get a momentum of positive 2,000 kilogram meters per second. Divided by the mass would give us the new velocity of the truck. Notice the truck is also moving to the right after the collision. If you've, again, watched some collisions, you see that the big object is going to keep plowing forward, and they will both end up moving to the right. Now, there's another way that we can look at this that's really going to be helpful because we don't always know those values of forces and times. But if we look at the whole system together, look what's going to happen here. So first of all, here I've got negative 5,000 as the initial momentum for the car and positive 10,000 as the initial momentum of the truck. So together, if I look at the whole system, add those two numbers together, pay attention to the signs, I get a positive 5,000. Now let's look over here after the collision. The car had positive 3,000, the truck had positive 2,000. When I add those together, I also get positive 5,000. Okay, this is not a coincidence. I didn't rig this problem. This is what happens with collisions, is that the momentum before equals the momentum afterwards. Why? It's because the impulses are equal and opposite. If you look at the whole system, the system felt a positive 8,000 and a negative 8,000 impulse. And so the net impulse, the overall impulse, is zero. There's no change to the momentum. So during a collision or any sort of interaction, so it could be an explosion or something like that as well, if you can find the momentum before and the momentum after the collision, those two numbers are always going to equal each other. That's looking at the whole system, multiple objects that you're looking at. In other words, momentum is conserved. And so we could use the similar notation that we used for energy, the sigma notation. And we can say that the initial momentum, notice the arrow there, pay attention to directions. Initial momentum equals the final momentum. But if we want to look at an individual object, its momentum does change. Okay, that is not like the same value before and after. And so we could look at its initial value, we could combine it with whatever collision impulse happens, and that would determine its final momentum. And then just a reminder that this was an earlier formula from this video, so I would take a minute to get all these jotted down as you move on to the next step in our discussions.